Good evening. Thank you everybody for being here so late in the day. Who's looking forward to the movie night? You want to stay? You can just stay right here as far as I'm aware. My name is Nikolai Parlok. I'm a Java developer advocate at Oracle, and today it's going to be you, me, and structured concurrency in action. Although the action will be somewhat limited because I originally planned this as a live coding talk, but then I realized I want to show you that much that live coding, all of that does not comply with how fast my fingers can move. So, I'll show you code even in an IDE, and I'll run it too, but I won't type it out live. I hope you're okay with that. Okay, so the slides are already online. If you want to take a look and follow along. Also, the code is online. You might see commits from just 1 or 2 hours ago. Ignore that. If you have any questions, feel free to ask at any time. You can raise your hand, and if I don't see you, you're free to interrupt me. Don't wait for me to take a breather. That doesn't happen that often. Before we get started, the structured concurrency API that I do want to show you is a preview API in JDK 25. That means that it's not final, it can still change, and it changes based on feedback that is given in part by the wider community, that would be you. So if you have the chance to try this out in as close to a production code base as you can, that's great. I'm not saying you should run this in production, even though you could. I'm saying try it out in a production code base, see what works and what doesn't, try to find the corner cases, the edge cases, do give feedback to the Loom dev mailing list. They would greatly appreciate that. And there's a link to JDK 25, but I'm sure you all know where to get it from. Okay, let's get going. I want to briefly go over a few slides, and we're going to come back to the slide deck occasionally. We're going to spend most of the time on the API overview and on the cancellation. And the back pressure and building blocks part that lean a little bit into the virtual threads, structured concurrency versus reactive part of this will be a little bit of a bonus, and we'll see to how much of that we get. I think it's in the most important part is for you to take away how the API actually works. So the fundamental starting point is that virtual threads are cheap and plentiful. You should not pool virtual threads because you should only pool expensive resources, which these are not. You can basically, whenever you have 2 tasks that you want to have to happen at the same time, create a virtual thread for each. Or you can just do that however many times you want, it's fine. The question, how many virtual threads can I have, is akin to the question, how many strings can I have? Yes, there is a limit, but ideally you can have as many as you want to. And once you run out, that is the time when you start to wonder, like, okay, maybe I've overdone it, maybe there's some memory issue, maybe there's something else I need to do. But think of it this way, just like you would create a string for every string that you need, create a virtual thread for every concurrent task that you need. There are other reasons, like parallelism and thread pools do still exist. I'm just specifically talking about situations for virtual threads. Okay, and this whole new thread per subtask allows a new programming model. As a first step, you could do something like this. I use here executors.new virtual thread per task executor, which returns an executor service that, as the name suggests, creates a new virtual thread for every task that you submit. And then you could do this, right? I have a task A and a task B, whatever they are, doesn't matter. I submit both of those, and then I get back something that is a future, or completable future even, and then you can get and wait for those results. This would be the quote-unquote normal way, unstructured way, just the way to use this kind of virtual thread everywhere kind of API. Except for the fact that it spawns virtual threads under the hood, none of this is new either. We can do much better than that though, and that's what we're here to discuss. Quick throwback to the 50s and 60s, when programming was basically writing go-tos that navigate through a sea of instructions. The idea was, came out of the way that systems worked before that, but in the 60s it turned out that this is maybe not the greatest approach. You probably heard about go-to statements considered harmful, this article by Dijkstra, that was 68. And the idea is that maybe doing just everything with go-tos isn't so great. Let's have specific control structures. Let's have entry points and exit points. Let's make this programming more structured. Structured programming, a term that he coined. And this stricter approach made our code so much clearer and better that, at least for me, and I think for most of you, maybe even all of you, it's inconceivable to program any other way. So this is what I just showed you, the same code again with a few comments in between, is unstructured concurrency. It's unstructured because there's a thread pool, or in this case, an executor service that exists somewhere, right? This could be a static final field, who knows where. Then you submit subtasks. Somewhere, if you get back completable futures, maybe you enqueue additional operations. You do that somewhere. And where do you get your results out? Also, who knows where, right? So it's not easy to follow the thread of concurrency through a program that is written like this, if you imagine this code exploded across like 300 different classes. Structured concurrency comes with this with the statement. When the flow of execution splits into multiple concurrent flows, they rejoin in the same block. We want to define a block, and in that block somewhere concurrency begins, and in that same block concurrency ends. So whatever you want to fire off to happen at the same time happens within this one scope. The term was coined by Martin Sustrick in this blog post and then later refined by Nathaniel J. Smith. If you do have the slides on your machine, they're both links, but also if you search for these names and these terms, you will find them. So that means the structured concurrency term is by no means invented by Project Loom. They just discovered that this concept and virtual threads work together really well. So let's lean in, let's do that. The thread lifecycle then, if you have this scoping concept, is pretty simple. Whenever a task begins, the thread starts, and whenever the task is done, the thread ends. Which is not true if you have, for example, thread pools, right? Then the thread lifetime and the task lifetime are independent of one another. This is no longer the case. The idea is you need a task, you start a thread, the task is done, you let the thread die. And what that means is that now all the threads that work on subtasks that belong to the same larger task exists while the larger task is kind of still waiting in this block, in the same block. So all the new threads become children of the thread that spawned them, and they are siblings to one another. And this relationship does not generally exist between threads, right? If you have a thread pool specifically, but also if you have just regular running threads that pass messages between one another, they do not have this relationship that one of them is the parent of the other, or that there are siblings and that you can just make decisions based on how one thread behaves. It's not like this is impossible, right? You have something like computable future where you wait for all results to exist, but this makes this more formal, more structured, and easier, and with accessible, and also gives it additional information that we'll see later. We're now going to see how this works in action, and for that we're going to use an API that I wrote to demonstrate this. So this is not the structured concurrency API. This is the API that we will use to perform tasks. So I have a class that is called task, and has these three methods. It has a run method that throws an IO exception. They also all throw interrupted exception. We're going to come back to that later, but because it didn't fit on the slide, I just left it out. So they all throw IO exception, meaning they can fail. And they run, and you pass in a behavior. We'll see that in a second. You pass in run successfully, take a second, fail after half a second, stuff like that. So we can configure and fiddle with it a bit. The run method just changes the internal state of the task. That is something, if you do not program in a functional way, a common way to do this. Fire off this task, and when the task is done, some state changed somewhere that I can maybe query. We'll also see that I have a compute method, and that one is easier to handle in general. It does the state change and whatever, but it will also return a result. And then in the end, I also have a rollback that you can use to reset the state. And we can see here how these states belong to one another. So I can create a task, I can launch it, and then it can either get canceled, it can fail, or it can complete. And it was canceled or failed, I can roll it back, and then it can be relaunched. Again, this is just the class that I wrote. But I wrote it this way because I think this is a fair view of what many tasks will be like, right? Real-life tasks will maybe be more detailed or don't have all of those states, but you can see how this probably maps on a bunch of things that you would do with structured concurrency. Okay, that's all that. Let's see some code. I knew I was going to do the wrong direction the first time. Okay, good. So let's start. I have a first step, like a very simple way to use this here. There's very little going on. The first thing that you do, or the main thing that you do when you use structured concurrency, is to interact with what's called a structured task scope. That's a new class that was introduced by this API. And the way to use this is you open it in a try with resources block. This is when I said when a task splits into concurrent subtasks, then this is the part where that happens. This is where the splitting begins. You open a structured task scope, and then you fork a bunch of tasks therein. You'd say this is a task and a subtask and a task that needs to be done. So that's what's happening here, right? The next three lines, you fork a bunch of things. They all just print line, so we can see like the simplest thing possible. And then join means now we'll wait until they are all done. And then join will have different behaviors depending on what kind of subtasks you fork, and it has error behavior. We're going to explore all of that. But for now, that's going to be it. And then there's one more implicit thing at the end here. At the end of a try with resources block, what method gets called on the resource? Exactly, perfect. Close gets called. So the structured task scope is closed. And that method waits until all those threads are done executing and returns. Wait, isn't that what join does? Not always, we'll see that. Whatever join does, this close part at the end there will always wait until all tasks are complete. And that's going to come back later to, you could say to haunt us, but that's not true, but it becomes important. Okay, good. then let's have a look at a proper use of this. Oh, I mean, we can run it. Let's quickly run it. Very straightforward. We get ABC. I hope nobody's surprised by this. Let's have a look at a more interesting task, which immediately runs us into the first little issue, which is not really with this API. It's more like with how runnable and callable behave. So what I'm doing here is the same thing. Now I create these 3 tasks because now I want to observe their behavior in a little bit more detail. I fork these 3 tasks, and now I have to do this like stupid return null dance here. The reason for that is, and I'm telling you this because you're going to run into this if you use the API, remember that run throws an IO exception, meaning a checked exception? That means the lambda cannot be a runnable. So the lambda must be a callable, but a callable returns something. But remember that my run method doesn't return anything. So I have nothing to return. So return null, that turns this into a runnable of void, and so it is what it is. So just be aware, this is a common problem that you have to deal with runnables and callables and exception throwing non-functional things that you call, meaning things that just change state and don't have a return value. Okay, so we're gonna try to memorize the structure. We're gonna see it again and again and again. We're running these 3 tasks. We're saying this behavior is to just run successfully for however many milliseconds. Then we're waiting here, and then we're gonna lock the formatted states. We're gonna lock what the result of this is. So let's see what this looks like. Maybe I have to give myself a little bit more space down here. So first of all, I extended my logger to include a V for virtual and a P for platform thread. So everything that says V is actually a virtual thread. We can see that after 200 milliseconds, roundabout, all these 3 tasks start, and then there's the end with like 100 milliseconds after another, because that's the times that I configured. And in the end, the state of those is all 3 completed, and then we're done, and then that's that, right? So I hope that none of that was in any way surprising. And this is how this behaves. Now, as I said, this kind of dance is kind of ugly. So I would recommend, if possible at all, do try to use this in an approach where the result is returned. The result that you're looking for is returned from your method. That's what I'm doing here. I'm calling compute instead of run, and now all of this becomes much, much more like readable. So what I'm doing here is, again, opening the task scope, I'm computing these 3 behaviors, and fork always returns something. Fork returns what's called a subtask. Now, the subtask also has a get method. And you might think, oh, I know what this is. It's a thread pool. You submit something, you get something back that has a get. If I call get, then it blocks. But no, this is not what this is. This is not a future. A subtask is something that has a state, we'll see this later, and that gives you access to its result. But you need to let it run its course. You can you can ask for the state in between, but you can't just get and then block. The way this API works is you fork all the subtasks, and then you wait in this join call. This join call is essentially, it means at this point I need to wait until the rest completes. It doesn't mean all threads are done. I'm going to get to that, but it means like the subtasks need to be completed somehow. We want to be done with those before I continue. And so let's run this one as well. Here I'm then formatting the results if I get to this, if there is no error. So let's quickly run this. And again, like there's nothing really happening here. Those 3 tasks get launched. You can see here a little bit of non-determinism by the order in which they actually get launched. It's not the one in which I fork them. You know, usual thread behavior. They're all complete, again, like roughly 100 milliseconds after another. And because they all work, I get this result here. So this success, let's briefly look at the method format results. It doesn't do too much interesting things. Again, you give it just like a couple of subtasks, and then it says, okay, let me query the state of each subtask, what they're in, success or failed or unavailable. Unavailable actually means they're not done yet. I should never run into this situation. I can query it maybe, but I should, in this case, this is not how I want to use this method. So it throws an exception. And then it just puts the results together. And the important part here is that I call subtask get at this point, right? So when it works, I call subtask get. But this is not, like you will not often have to switch over the state. You might not even have to get the result explicitly. This can happen. I'll show you cases where. But something like this is not something you usually want to do. Okay, so this is how this method behaves. Let's, oh wait, this is actually the different class. Okay, so I hope this is all straightforward now. So we're forking 3 subtasks. We're computing this kind of result. We get the results back. We're formatting it. Everything works. Now, what I want to do now is I want to show you what I said earlier, that this relationship between tasks, between threads, is important and relevant. I'm doing the exact same thing here, except that I take, instead of 100 and 200 and 300 milliseconds, 10 times that much time. So 1 to 3 seconds. And after about 500 milliseconds, when I'm sure that all 3 threads actually started, I want to create a thread dump. It's a different thing. It just creates a thread dump. And then we wait and we format the results. The interesting thing here is not the actual result of this call, but the thread dump. So let's have a look at the thread dump. Let's look at it here, threads.json. So if you want to check out how exactly to do a thread dump that is formatted as JSON, have a look at the repository. It's not that essential here, just a new command line flag that you, or new commands that you use there. This is a JSON thread dump, and it contains thread information, right? It tells you what each thread is doing. Somewhere here is this is root. This is like the main thread is somewhere in here that runs the entire operation, and all of these are doing different things. Let's not look at it too closely. What I want to show you is, and I know that they happen to be at the bottom, is this container here. So here we have a new thread container, and all the threads in here are virtual. And this is the code that I wrote. You can see here that this is my Lambda. This is the compute method that I always call, and that happens to call run, and that happens to call sleep, because I'm not actually doing anything. I'm just sleeping for a while. We can see that again, how that becomes important. But all of these three threads are here. And the interesting thing about this is that they're all in one container. So now imagine you have a problem. Imagine some bug raised its ugly head, and you do a thread dump. You can immediately see that these are not just three random threads. These three random threads belong to one group and do something together. And more than that, they do have an owner. So this is the owner of this container. And that means somewhere in here must be a thread group with a thread with thread ID 3. And here it is. This is the main thread that ran into the scope where it forked and then joined. And you can see that because it's sitting in StructuredTaskScope impl join. So that means you can have maybe a breakpoint, although this is not, as far as I'm aware, available in any debugger yet. But let's say you do a thread dump and you spot a problem somewhere deep down in a virtual thread. You can now, through this mechanism, go not just look at that stack, but also at the stack of all its sibling threads. And then you can navigate to the next thread up if that's necessary. And if that's also a virtual thread that's also sitting in a StructuredTaskScope, you can imagine how this goes further up. So this is the relationship that I described earlier, and I think this will become essential to debugging. This is basically allowing what navigating through different stack frames in a debugger. This will be the same thing, but for threads. You'll be able to not only go from one thread to the other, but you will understand why do I have to, what thread am I looking for? Why is this, how is this thread related to this other thread? So I think this will become an essential ingredient in debugging applications. Okay, good. Now let's start breaking things, at least a little bit. So this is the same example as before, no thread dump anymore, but I'm failing after 200 milliseconds. So let's see what the result delivers here. So I'm running these things. And now, after 100 milliseconds, task A completes. And then another 100 milliseconds later, task B fails. Immediately, millisecond later, I get that task C was canceled. And then I end up here in this failed, this is the exception that I'm catching here. I'm ending up in this log error message here. This is why this is called an error. But this is an error. And then the states that I get is thread A completed, makes sense. Thread B failed, makes sense. And thread C was actually canceled. I'll show later how this comes to be, but this is important. Apparently, the task scope wants all threads to succeed. And if one of them fails, we basically throw our hands like, okay, we can't do anything anymore. Let's cancel all of this, which can be important. Like if you need everything to succeed, why continue doing something that you already know is useless? And this is the kind of overarching error behavior that is really simple to achieve with structured concurrency. Okay, then let me see how, the next thing is how would you roll this back? How would you do error handling in general? So the thing is, if I'm here, and if I go here and I want to deal with a subtask, I can't, because the subtasks are scoped to this try with resources block. That is kind of annoying. The solution for this is unfortunately a nested try block. So we're going to see a better solution in a minute, but this is the general solution that works. You join, and then join will say, oops, something broke. And now, if you don't have any additional mechanism installed, it's up to you to figure out what failed and handle it. Clearly, that is always possible. Also, clearly, this is very uncomfortable, and we ideally don't want to do this. So what I'm doing here is I'm trying to figure out which of the damn subtasks failed, so then I can roll all of the failed ones back. And then I want to format the error result. Format the states. So if I do this, now I get that task A completed B failed, C canceled, and then B and C, both of them reported that they rolled back, right? Because I called rollback. The ideal way to go around this, which I think is most often open, but not always, would be a method that does it on its own. So if a task can roll back itself, that would be ideal. We're now inside the task class, and compute or rollback does what it says. It tries to compute the thing, and then it catches exceptions itself. It tries to figure out what, like, it is aware of the fact that it can fail, and if it fails, it tries to undo. So you can, for example, see this, maybe they have an operation that writes something to the file system. And then at some point it fails, it's like, okay, I have to clean up after myself, I delete a couple files, or whatever else that would be done for rollback. If you need to do rollback, ideally the task is capable of doing it itself. That is not always possible, as I said. For example, maybe it needs information from other tasks to do that. In that case, you have a little bit more work ahead of you. But generally speaking, this approach is usually available, and then it's usually much more comfortable. So with that, we can do this. This is much simpler now, right? So there's in this catch block here, I have access to the subtasks, but honestly, I could do subtask stuff here, right? But really, I don't need it even more. So I don't need the second try block here. I could basically go back to the other approach and just have one try block. So this does the same thing as before, but the rolling back now happens internally in the tasks. Good. Okay, so that explains the default behavior of the structured task scope. It starts with the open call. You fork several subtasks. Then at some point you join, and unless I'm making a mistake, oh right, yeah, you cannot fork after a join because in the join you're waiting. You cannot fork from a different thread either, by the way. You cannot spawn another thread that then forks tasks to the same scope. The idea is, remember, it's all happening in one scope. So on open, you open a structured task scope. You fork off a bunch of subtasks. You sit in join and wait. And ideally, the join call returns regularly. Then you do result handling. You return something, whatever you want to do. In the non-ideal case, in the error case, you catch the exception and do something with it, and then you're done. And by default, it wants everything to succeed. Now let's have a look at that last one, and let's go over a little bit over. Maybe you don't want anything to, don't need anything to succeed. TaskScope.open accepts what's called a joiner. I will show you later what the joiner API looks like, but for now, a joiner is in charge of managing basically the state of these tasks. It gets informed when something happens, and it needs to figure out what the desired error behavior and what the desired result behavior is. This is done for heterogeneous tasks, meaning tasks that return different things. Now, all my tasks happen to return strings, but let's ignore this. All these are subtasks of string. Let's ignore that for a moment. This could be the first subtask grabs a user, and the second one grabs a basket. And then the third one, you know what I mean, right? You put something into the Warenkorb. The cart, exactly. Thank you, not the basket. So right, you can see how this grabs different things and then combines them. So this could be different return types. And I want all of them to be successful, or I throw. So this is the behavior here. I have different kind of tasks, and I need all of them to succeed. This is the default behavior. This is what we saw earlier. I didn't change anything except make the code a little longer and more explicit. And it didn't work because here it says I want to fail. And if I don't want to fail here, if I want to run successfully here, then I'll see this all succeed. Okay, so far so good. Now let's see what else we have available. Let's say I want all of them to be successful, but I also know that they all return the same result. They all fetch a user, or in this case, they all produce a string. That's a nicely formatted case that's somewhat simpler. And the joiner allows to deal with it. I can create a joiner that's called all successful or throw, and it needs to know what kind of result we're producing, which means I need to pass in, this should be a joiner of type string. Okay, so I fork these three subtasks, and then when I'm done, join now actually returns a stream of these subtasks. It returns a stream of subtask of string. And because I know they were all successful, because otherwise I wouldn't be after the join, I can get all the results out. I can collect them with the joiner result here, and then these do run successful, so then we can see that code working. So this joiner result that we see here is what's happening here on line 68. Okay, so I'm making use of the fact that all the results return the same result, same kind of result, but I still want all of them to succeed. That's not maybe necessary. This one, any successful result or throw, It's like the other one before, but only one successful result. So the joiner can configure that. The joiner can say, oh, one of them failed, that's fine. Another one failed, that's fine. The last one failed. Now we're in trouble. So if all three of those fail, we will actually see the task scope, sorry, the whole thing as a whole fail, right? So I ended up, see that's an error message, that means I ended up here. But if I undo this last fail and I do this, I get different behavior. So the first task complains that it failed and wrote itself back. The second failed and wrote itself back, but the third one completed. And that's all I need. Then I end up here, and then join now returns the single result. It just gives you, here's the one result that you asked for. That also means that if I have several of those, and I run this, now I will see task A failing and rolling back, task B, because it's the next slower one, being completed, and that's also the result that I'm getting. And at the same moment when B completes, C cancels, or C gets cancelled, right? Because I don't need that result anymore. So it gets immediately cancelled, and then it rolls itself back because of the whole error, the whole making sure that the state is clean situation, and then I'm done here. I hear the chatter picking up a bit. Do you have a question? I mean, you can chatter, don't get me wrong, but maybe I'm not explaining something well? Yes. If you want all to complete, and you only want to get successful results, okay, that leads a little bit into the next one, but I don't think it's quite what you're asking for. The next one says, wait for all to complete. I don't care what comes out of this. But then also the join doesn't return anything anymore. This means I have tasks that have different returns. Just let them all go, and I will figure it out later. So for more complicated scenarios where you say I have like 4 subtasks, and there are certain combinations that work, and other combinations that don't, and that is business logic, you probably don't want to put the business logic into a joiner unless it's very common in the system maybe. You could then figure it out yourself. But those are the joiners that are available. Do you have more questions? Feel free. Yes, absolutely, thank you. I did not pay these people. There we go. Wait, what? Where is it? Oh, it's not exactly the next one. I thought it was. Okay, you know what? Let's skip this one because it's a little bit specific. Let's go to the one where you want to write something yourself. Here, I'm passing my own joiner. It's called an until joiner. Why is it called that? Doesn't matter. Let's not look into this thing, what it does actually too deeply. I want to show you how it works. This is a joiner. It has an onFork, onComplete, and result method. The way this works is every time you call fork, the StructuredTaskScope creates a subtask and then passes into onFork. And then onFork can do something with it. I'm calling super onFork here. I don't need to. This is basically an empty method. But, it's like this one is also, I think it's not doing anything, right? Oh, well, almost, but not much. I think it's fair, like I don't need this, right? This is just, because onFork is a default method on the joiner interface, I could just leave this empty. I just have it here so I can show you. Then onComplete, you can guess, right? It gets a subtask onComplete. And here I don't know whether it completed successfully or not. I have to figure that out if I care about it. So this is, here I'm having a specific predicate that I'm calling. Don't look into the details, it doesn't matter. The point is, I can signal when I'm done. That also works with onFork, by the way. You can return true to say we're done here. We don't need to do anything anymore. And when we're done, the StructuredTaskScope takes it as a signal to cancel everything that is still running. And then result gets called. And my joiner happens to return an optional of subtask. Your joiner can return something else. And then the result method either returns that result or it throws an exception. If it throws an exception, then StructuredTaskScope.join keeps throwing that exception. Okay, so you called fork, the StructuredTaskScope creates a subtask, files it through this onFork method, and you do some bookkeeping or whatever else. You can return true when you want to say we're done here. Same thing on complete, when a subtask completes successfully or through an error, doesn't matter. It gets fed through this method on complete. You do some bookkeeping, you can return when you're done with return true. And then in the end, result gets called. And then you say, either return my actual result or throw the error that I want to throw. This is how you create your own joiner. Okay, I said a bunch of types. I want to move on from the core API, from StructuredTaskScope on joiner. Is that okay with you? One more question there? That I swear I don't pay these people. But the answer to that is absolutely yes. Let me quickly find out where my cursor is. Let's talk about cancellation. Okay, there are two kinds of, I mean, there's all kinds of ways to say there are two kinds of methods. I want to say there are two kinds of methods. One of them just depend on local resources, right? They have like, you have the data maybe on disk, otherwise in memory, CPU, you do some math, whatever. You have another kind of method that is blocking. It's waiting for some external event. That could be a WebSocket. That could be a timer that runs out. All kinds of things you can imagine. These are blocking methods. The issue with blocking methods is they may take a very long time, or worst case, even never occur. So it would be kind of good if you could somehow tell that task to please be done now and fail, but don't, keep doing this forever. And the way that this is implemented in Java is through interruption. Interruption is that cancellation mechanism, and it happens on the level of threads. That means threads can be interrupted. And it is a cooperative approach. You might know that there's like thread.stop, then you might also know that that is actually getting removed right now because that is not the way that this is supposed to work. The JVM is not in the business of managing threads that way. You are, or like at least our code isn't. Our code is in the business of trying to solve a problem, and the way that thread interrupts work is you tell another thread to please be done, and then that thread might ignore you if you're not handling interrupt exceptions well. Okay, so interruption is that mechanism. There's two parts to this API. One part are the methods on thread. There's an interrupt method, and all that really does is it sets a flag. It sets the interrupt flag. It's a Boolean flag. It doesn't do anything beyond that on its own. You can check that flag with is interrupted, and also very annoyingly, there's a static method. I find that very annoying because it's easy to make mistakes with it. Interrupt and is interrupted are instance methods on thread. Interrupted is a static method on thread. And it basically calls on the current thread, are you interrupted? And then, by the way, while doing this, also resets that flag, which means like you have to really process that information then, or otherwise it's lost. And the other branch of this mechanism is probably the one you encounter the most, which is interrupted exception. And the common way that this works is that blocking operations, particularly those ones that behave well within the JDK, if there is a blocking method, it will observe that flag, and once it's set, it will throw an interrupted exception. You've seen this. Oh, I'm writing a little script. I want a thread.sleep here, 100 milliseconds. Oh God, I have to handle the interrupted exception. What do? Try, catch, ignore, I guess. Interrupted exception is very annoying, but it's also very important. It means something very significant. It means that you are doing a long-running task, and somebody asks you to please stop doing it. And if you just catch that exception and ignore it, this information is lost, and you can just keep computing, which is not great. So if possible, when you catch that exception, stop what you're doing, maybe undo steps if that is essential, and then probably throw that exception up stack because the method that called you also needs to show that it was interrupted. So that might mean a lot of interrupted exception. I'm aware that's not great, but it is the way that this needs to work. It's already that way, but structured concurrency leans on this. If you do not have a chance to rethrow the interrupted exception, please reset that flag. So that code that does check for this can at least see it. Okay, StructuredTaskScope does support cancellation. I said it a bunch of times, a joiner can cancel by returning true out of that method, and then the StructuredTaskScope goes through all still existing child threads and sets the interrupted flag. And if they process this correctly, that means that then all these subtasks can stop computing. If they just eat the exception and keep running, we don't get the desired behavior. We'll see that in the examples in the code. Nope, wrong version again. Okay, let's go to interruption. There we go. Okay, so give me a sec. There we go. Okay, let's run this. Okay, so as I said before, or as I showed you before, we've already seen this example, by the way. It just computes a bunch of things, and one of the tasks fail, and then another task gets canceled. Okay, so now let's look at this. How does it get canceled, actually? So we go look at compute. Let's close the thing down there. Then we look into run, because that's the actual thing that's happening. And run has, like, the first part is just a little of state checking. It has this behavior class, and because I'm a data and programming geek and want to do it everywhere. I did it here too. This is the thing you pass in. The run behavior, the busy behavior, specifically you pass in fail. And fail just thread sleeps for a while and then fails. So this is what my code usually does. The important part here is this. Let's say thread sleep were not that. Maybe thread sleep is ask the database, query web service, something that blocks, something that throws an interrupted exception. So your task calls something that says throws interrupted exception. That the compiler then forces you, unless you want to rethrow or keep throwing, you want to catch that interrupted exception. And what I'm doing here is I'm setting the state to cancelled, and I'm logging this info here. The whole, the state of the thread is cancelled, or of the task, the state of the task is cancelled, and the task tells you that it got cancelled. All these messages that we've been seeing here, this is not coming out of nowhere. This is exactly the code in that catch block. So it handles this cancellation by doing exactly what I told you, what I just said we should do, which is stop doing stuff. And we're saying, okay, I'm basically cleaning up my state, so to speak, telling the world about whatever, and then I keep throwing, right? Okay, so that's how you properly would handle this. And to show you, I want to show you how this is important, but I also want to show you that this can absolutely be nested. This is just a very brief mention, but it will become important if you actually do this in practice. This is by no means limited to just doing this once on one level. You have one structured task scope that fires off new tasks, and that's it. No, this absolutely composes. So if one of those threads ends up in a situation where it once again needs to do several things, it can open a new structured task scope with possibly a different joiner that has different kind of error behavior. Maybe the top tasks need everything to complete, but the subtasks only needs one of the things to complete. And this behavior composes in the sense that here I have this inner method, by the way, which fires off two other tasks. So I have an outer scope that does something successful, and I have an inner task that failed, one of the tasks failed early. And they all have this everything needs to succeed behavior. And if I run this, I get this behavior that they all three launch, and then one of the inner tasks fails. All the other tasks get cancelled. That means this task scope here, this method that I've spawned, down here, that's the confusion. This task that I spawned here, it fails. And that means that this join method will then throw an exception because, something failed. And so this throws an exception, and that means that this task in the outer task scope catches that exception. And the joiner says, oh no, everything needed to succeed. So that's how this specific behavior composes. And if I would now say here, let's say joiners, and this is not planned, so I'm probably going to do it wrong. Which of these was the one I was looking for? Any successful result or throw? Oh, no, wait, that's not the class though. No, it's a new. Join. Yes, maybe joiner. Wait, I swear I've done this before. Yeah, I need to go somewhere, but before I'm there, I need to get the name right. Joiner dot. This looks right. Isn't it not imported? Oh, it's not imported? There we go. Okay. And then, yeah, that should be it. Yes, okay. Yes, I could put string here, doesn't matter because we don't care about the return really. Now I hopefully see different behavior where the whole thing kind of succeeds. So the C fails, but because B completed, and I only need one of them to complete, this task completes successfully, A completes successfully anyway, and so I end up in this situation where I format results. See, there's no error log message here. So even though one task failed, and the messages are not lined up well because they were not made for this case, but even though one of them failed, it's fine. As I said, it composes well. Okay, I want to get to the case where we misbehave. So let's go to this one. This is the same example as the first one. I have two runs and one fail, and I want to see the whole thing fail fast. And that kind of happens. I launch all of them after 200 milliseconds roughly. Then A completes, B fails, and then the whole thing errors out. And after so when B fails, immediately after, I'm here. First of all, note the absence of thread C failed. Again, this is not an automated message. This is something that I put in the code explicitly, and it doesn't happen here. We'll just figure out in a second why. And if I query the states, indeed, it's in this launch state where it's apparently busy, but it doesn't stop. And worse, look, it completes 800 milliseconds later, and only then are we done. Only 800 milliseconds after we knew what the result would be, did we exit the try block and come to this log message. And the reason for that is that, well, one, at the end of the try block, we're waiting for close, and close will be only done when all the threads are done. And the problem is, if I call run busy, as I did here, I do behavior that if my code does, oh, that's not the one I was looking for. If my code does not just sleep and fail after, it's probably this kind of behavior, which is just, let's do a busy while loop. I'm sure this is fine. So this code does not sleep. That means, or does not call a database or whatever. That means nobody throws an interrupted exception. And the code itself doesn't check the interrupted flag. And so this is the behavior that I get. A way to fix this would be, for example, to, in this loop, say if thread.current thread.is interrupted, then let's throw a new interrupted exception. Oops, that's not how you write through. Almost, off by one. Okay, let's go here and let's run it again. And I get the same behavior. Like I didn't do the reset and everything right here. But the point is, I'm done 800 milliseconds earlier. And the reason is, I properly treated this scenario. So that means, if you are in a situation where something throws an interrupted exception, take it seriously. If you are in a situation where you know this is probably going to be used in some of these scenarios, and I'm doing like a really long-running, really busy computation here, consider checking is interrupted occasionally. You know, at the end of a loop, or you know, you find places that make sense to check this. You don't need to do this eagerly, right? I would not say every long-running computation now needs this if check at the end of it. That's not what I mean. But be aware this is a thing, and then if you write something that's either used in this context, do it, or keep it in mind, and for the case that you end up in a situation where you do not get the abort early behavior that you were hoping for, then remember, oh yeah, maybe one of those threads isn't checking this. Maybe it's just running forever. Okay. I showed you earlier how you can put into the structured task scope a joiner. What you can also do is you can add a configuration. This configuration can do a few things. One of the things you can do is you can set a timeout. And the timeout is for the entire block. So here I'm setting a timeout for 500 milliseconds, usually expected on something like a join, right? Yet that's usually where this kind of timeouts go. But the idea is, what if this up here takes a little bit of time? It's kind of like you probably want to configure the overall length of the thing, not just the length of how long join waits. So that's why it had to move up there. That's one of the things that maybe, depending on feedback, might change. I think there's actually already a JEP for JDK 26, and it might have changed, but I'm not sure. The point is, running this, we're again doing run busy here, but now it behaves better, so I hope to see the right behavior. So there's a timeout after 500 milliseconds, and that means that I launch this at around 200, and around 700, we just time out. So I get this timeout exception here. So that's another exception that StructuredTaskScope.join can throw, a timeout exception that tells you, you asked to be done in 500 milliseconds, I'm doing that for you, but it's communicated via exception. Just quickly on the configuration stuff, you can not only configure a timeout, you can also configure a thread factory, for example, to give every thread a name, but also maybe you do want to have this as platform threads, maybe, right? This is also functionally working. It's just a question like how many platform threads you want to create. But you can configure a thread factory that does the thread factory things. You can also give this whole scope a name. So if we run this, and then we look at the thread. Oh. We look at the thread dump. We should see what was the term important? Did I put the important? There we go, important scope. That's this one. So that makes things obviously easier to find, right? In your thread dumps. And that is the end of that. Now, we do have these two topics, back pressure and building blocks. We have 5 more minutes. As I said, I want to really make sure that you took in the way the structured concurrency API works. We're done with that part of the presentation. So you've seen how it works by default. what a joiner is doing, how to configure it, the importance of interrupted exception, and that's the general concept of open, join, and close. Do you have any questions regarding that? There's one up there, yes. Yes. How well does the output of a thread dump scale? That's a very good question. Wonder how well does this drop-down box in your IDE scale for the threads that are there? So yes, this is a challenge actually. It's a challenge for tools who are used to like hundreds, maybe thousands of threads and finding so many more, and that means the tools probably need to get better, right? Like IDEs often have a drop-down box to when you're in a breakpoint to select the current thread. This is not scaling anymore. Like a drop-down box will just like explode your UI. So tools need to be updated with that, but there's just no way around it. If you have 1 million threads and you do a thread dump, you want to see all that information. You don't want it to be truncated. So whatever tool you have needs to handle that. Maybe they need a tool that can open JSON that is larger than a couple of megabytes. That could absolutely happen, yes. Okay, let's talk a little bit about this. First of all, grain of salt. I do not actually know what I'm talking about, generally, but also reactive programming. So I might tell you things that I have this checked. I'm somewhat confident, but if you think, no, I know better, this is definitely different, then you might be right. So if I make a mistake, please let me know. I looked at reactive programming frameworks and what they say about themselves, and a core feature there is back pressure. That's something that reactive frameworks tell you about. And that's also something that often comes up when you talk about using virtual threads, using structured concurrency to replace or to not really replace, like nobody's proposing that you just go through an existing code base that works and just refactor everything to StructuredTaskScope. But to replace in the spiritual sense of the next project, maybe it doesn't use reactive streams, maybe it uses virtual threads and structured concurrency, then the question often arises, but what about back pressure? I need these back pressure mechanisms. And there are 3 kinds of situations where you need back pressure: between operations, between threads, and between processes. If you have one operation, meaning one method in Java, producing something that the next method needs to consume, you already have back pressure. Now, nobody's going to jump one method to call the other one first, or to call the other one before the first one is done. Unless you have some async where somebody puts something into a queue somewhere, between operations, back pressure is automatic. So that's good. If you want to do that between threads, then you can use queues for that. It says more on queues in a minute. I doubt that we get to that. So I just want to point out that there are a bunch of queues in the Java collections framework. And the things that are not there, you can either wrap around them and program yourself. There are examples, and I want to point that out, it's not production code. There are examples in this code base. But also there are other libraries that do that. So if you need to have different threads communicating things with one another, and you want to make sure that one thread doesn't overwhelm the other, you can talk about queues. Do the queues block? Do the queue drop elements? Do they drop the first elements or the last elements? All that's something that you might want to configure and that you might want to that you can do through queues. So if you want to do that between queues, threads are if you want to do that between threads, queues are there for you. Not the only mechanism, but an important one. If you want to do this between processes, so across different web services, for example, then the JVM isn't really concerned with that too much, right? Like it's different JVMs running, so there's no inbuilt mechanism between that. But it kind of happens on its own with the right architecture. If you have within a system, you balance it well and it deals with it, it handles its resources well and doesn't just randomly die, then it will just stop accepting connections, for example, that push in new work. And then the service that pushes that in has to react to that appropriately. So it's not, so between processes, you have other tools that do not need to be handled by the JVM. There are different backpressure strategies. I already mentioned them a little bit briefly. What do you do when the buffer is full? You can block the producer, you can signal to the producer that something is going on, you can drop items, and all of that you can do through queues. I do want to show you code originally here, but instead of doing that, I'm just going to skip that. Basically, I'm showing you how to put a queue between 2 different threads and then use this to get certain kinds of behaviors. I have 35 seconds left and it's blinking at me red. I'm going to try to get through these building blocks. I didn't learn anything since the last caveat, so just keep that in mind. Reactive streams are often non-blocking, event-based. They use these backpressure strategies, streaming APIs, and they have these reusable operators. And I think virtual threads and blocking data structures and StructuredTaskScope can do a bunch of that, but the reusable operators are an interesting piece. I'm never met somebody who told me like debugging reactive pipelines is fun, I want to keep doing that. But I do meet people that say using these APIs and being able to have one call that says everything before here, I want to handle errors like this, I want to have certain retry behavior, all of that. That is important to me. And that is, I think, a good argument. Those reusable building blocks should exist. And to a degree, they do exist. Some things are just language constructs. Error handling is just try with resources. You don't need an operation for that. Java already has a language construct for that. Some map to data structures like the queues I mentioned. Some are available in other libraries. Specifically, something that I tried out is Resilience for J. You can see all the examples in this code base, which uses Resilience for J, which work with virtual threads to use something like a bulkhead, or I hope that's the right term, or thing that opens and closes. Circuit breaker, yes, the door, but also circuit breaker, exactly. So virtual threads do work with that, specifically with that library. I'm not here to recommend that specific library, but look into what you're already using, what building blocks already exist, do they work with virtual threads. So if you need a circuit breaker, you don't need a reactive stream pipeline for that. You can just use virtual threads and structured concurrency with a circuit breaker from Resilience for J. Okay, I don't want to keep you any longer because my time is up and it's late in the evening. Thank you very much for being here and spending your time here at Devox. If you have questions about any of the things that I skipped, do feel free to haunt me down here. I'm also here tomorrow, first half of the day. And I'll see you all around.